Welcome to AP Biology. We are now in chapter 2. This is all about water and its properties and how that water is very important for different life processes. And when we're talking about water, we need to talk about the atoms that make it up. It's called H2O, so it has 2 hydrogen and 1 oxygen. And when you talk about atoms in terms of their individual particles, it's made up of protons and neutrons and electrons. Protons are positive charge, and that's where we get the atomic number from. Electrons are negative charge. That's where we can balance between the positive and the negative charges, and the electrons are also the ones that are the very outside ones are the ones that are available for chemical reactions. And then inside are also neutrons, which have a neutral charge. When I say inside, atoms are made up of a nucleus. Let's not confuse that for a nucleus inside of a cell. And it also has an outer shell, mostly made of empty space with electrons zipping around. When we want to describe the atom, we want to describe it in terms of particle charge. So hydrogen is going to, and oxygen, both are going to be neutral because they have the same number of protons as they have electrons. So unless they are an ion, they're not going to have a charge. They're going to be neutral. In terms of atomic number, hydrogen's atomic number is 1 because it has 1 proton, and oxygen's atomic number is 8 because it has 8 protons. In terms of atomic mass, we count the neutrons and the protons. So when we want to add up for hydrogen, it's an average of 1.004, and that's because it has 1 proton, and normally it won't have neutrons. And in terms of oxygen, we have 8 protons and about the same number of neutrons, giving it about 15.9 as its average, so its atomic mass is about 16. And then in terms of valence electrons, hydrogen will have 1 valence electron, and so it wants 1 more to be more like its buddy helium. So it will share and be a covalent type bond. And a hydrogen bond as well is another name that we're going to be using. And in terms of oxygen, we have 8 protons, and so we're going to have 8 electrons. 2 are going to be in the center. So if you have 8 and you have 2 in the center, that means there's 6 on the valence electrons on the outside. So it wants 2 more to be more stable, and so it's going to most often share or try to gain those electrons to become more stable. So let's talk about bonds. Well, we're talking about water, so we're talking about hydrogen bonds and covalent bonds. So hydrogen is going to be covalently bonded to oxygen in a water molecule, and that means that the electrons are being shared between them. But because it is water, and you just have it between hydrogen and oxygen's going to have those electrons more often. It's the bigger brother that's not going to really want to share evenly. So that creates a charge where you have a charge on the oxygen end that is mostly negative and a charge on the hydrogen end that is mostly positive, making it a water molecule a polar molecule, which will give it a lot of characteristic that we need to talk about when we're talking about water. As far as the bonds go, we said they're covalent, but we need to talk about the other bonds as well. There are ionic bonds out there where you have a metal bonding with a non-metal. So like sodium bonding with chlorine, where the sodium gives its electrons to be more stable, and so chlorine will gain electrons to become more stable, and then they create a very one of the strongest bonds out of all these. You also have, like I said, covalent bonds, which are both polar or nonpolar. Water is polar, but then there are covalent bonds that are nonpolar, like your oils, for instance, where they don't have a overall charge on one side and an opposite charge on the other side of it. Think of if you kind of put a dividing line down the middle somewhere. If you can have a positive charge on one side and a negative charge on the other side of that line that bisects it, then you could say it's a polar molecule. That has a lot to do with how it will dissolve, how it reacts with other compounds and molecules. So it's important to know whether it's polar or nonpolar. Also, there is van der Waals interactions, which are a weaker type of bond, and that bond is used to help explain things like why a newt or gecko is able to climb on the glass because it has temporary bonds based on those uh, molecules zipping across each other and creating temporary static charge clinging going on. And so water is able to have this type of interaction as well as hydrogen bonds because it is a polar molecule, and sometimes those poles will line up with each other and have a static clinging to each other. And then you have what we said, hydrophobic, phobic being scared. So you're scared of hydro, water. So oil and water, for instance, don't mix because they have hydrophobic interactions. One of the other things we want to talk about is describing the role of molecular bond in the formation of compounds and distinguish among strong and weak bonds, giving biological examples of polar covalent, nonpolar covalent, and ionic and hydrogen bonds. So we said with polar covalent, water is a perfect example where it has the reason why it is your universal solvent is because it has both a positive end, which could attract to positive ends of other molecules, and it has, negative ends of other molecules because opposites attract. And then the negative end of the water molecule will interact with the positive ends of other molecules. So it makes it this universal solvent, able to dissolve whatever that charge is on those molecules and attract those to itself. A nonpolar covalent, you want to think about like oils and things like that that are nonpolar. So if you, for instance, want to wash oil off of something, water doesn't really work too well, but soap does, and that's because soap is also nonpolar. So when we're thinking of things dissolving, we like to use the phrase like dissolves like. So we're using soap to help wash off oil because you got two nonpolar things working together there. And then and both of those are covalent bonds, which means that you are sharing those electrons, not transferring electrons, and as opposed to ionic bonds, which you have gaining. One is gaining electrons, and the other element is giving those electrons. So we have transferring of electrons in ionic bonds, and those are like the strongest bonds. So think of salt that's made of sodium and chlorine. And then you've got hydrogen bonds, which is in water. So water is both a polar covalent bonds and it has hydrogen bonds going on between the molecules. It's not a it's not like permanently combining the two. It's just the bond between two molecules, and it's kind of temporary. But because they're close together and they have those opposite charges, they kind of stick to each other. So that gives water some interesting properties. Here's some 9 properties of water I want you to be able to list out. It is a powerful solvent. We call it the universal solvent because it can dissolve things because it is a polar molecule. It is very cohesive. So due to those hydrogen bonds holding water together. Cohesive means that two molecules of the same kind are attracted to each other. So this allows water to have a lot of properties, like this surface tension you see in the picture on the right here. Those molecules, water molecules, are so tight together that it's able to create sort of this skin across the top. It also allows things for capillary action. You've ever noticed when you're looking at a, let's say, you're looking at a graduated cylinder and you got that, what we call the meniscus is what we're measuring. It's the water seems kind of curved and you want to measure at the bottom of that meniscus. Well, the water is being drawn to the sides of the container um, of that graduated cylinder. That we would describe as adhesion, because you have the sides, which is made of one type of molecule, and the water made of a different type of molecule. So adhesion is those hydrogen bonds to other things other than water molecules. So that helps explain why, water seems to stick to us, so to speak. It has capillary action because of that. It also has high surface tension. That's more to do with the cohesion, and it has a high specific heat, which allows us to use water as a means to regulate our body temperature. We can start when we start sweating, and that sweat evaporates off of us. It carries all of that heat off and cools us because of that high specific heat and high boiling point, a high heat of vaporization. It is a good evaporative coolant just because has high specific heat and high boiling point, and it has a high freezing point. And this is the kicker here. Because it has low density in a solid form, unlike other elements, most elements, they become more dense when they freeze, but water doesn't. It becomes less dense, which allows organisms to continue to swim and survive in water when it freezes. Because that water, when it freezes, floats to the top, creates this insulating layer that keeps the rest of the water below from freezing solid through. So you got fish and things can swim around underneath that solid top insulating layer, so that everything doesn't get frozen along with it. It'll make one big popsicle. And also, because it has great evaporative coolant and all of that, it allows water to basically regulate Earth the entire Earth's temperature. So water and its properties are very important in biological processes. If it didn't have those properties, uh, you wouldn't have things like regulation of Earth's temperature. You wouldn't have things like an insulating layer above when it freezes, keeping the fish alive. You wouldn't have things like the chemicals inside of us being able to dissolve and be used uh, in those processes. That's why we're 70% water, because we need those solvents. And all these other properties, like the capillary action in plants, allows water to travel up without creating some kind of pump, allows the water to travel up to the leaves. So we described how the unique physical and chemical properties of water are used in earth processes and biological processes. Also, another thing to mention is water's use in pH. pH is, when you think of water, not tap water, but just regular distilled water is actually neutral. It's the center of the pH scale. It's a 7. And so it has the right amount of hydrogen and in there. Um, Then you've got H3O, which has one more hydrogen. That makes that going have be lower or more acidic on the scale. So you have those hydrogen molecules, moving back and forth and going from H3O to H2O, and also going to just causing water to be neutral overall, but going back and forth between acidic and neutral and basic. So this is where the pH scale starts to come in, because you got these things dissolved or disassociated in water, these hydrogen ions disassociated in water. So if you have more hydrogen ions disassociated in water, then you're going to be more acidic. If you have more hydroxide ions, that's the OH, disassociated in water, you're going to be more alkaline or basic. Well, all plants and animals have a certain threshold that they can withstand a sort of pH scale. So too acidic, it can die, or too basic, it can die. Too acidic, the enzymes that we need start to fall apart, or too basic, they start to fall apart and not work. For instance, these plants here, if acid rain comes down, you go from left to right here in this picture. The reason why the plant on the right is so has fewer leaves and starting to brown and die is because it's been sitting in a pool of or ground saturated in acidic rain. So when the pH is too high, it can't just move off and plant go away from that and get fresh water. No, it's pretty stuck there, and that pH being uh, too low, more acidic, causes the leaves to fall off and it to brown and die. Well, the same thing happens to the fish that are in the water. They'll die from that acid rain, or if the water becomes too acidic or too basic. So you need this perfect thing. So what does nature do about it? Well, it creates these things called buffers. They have buffers within their cells or within their biochemistry that allows the threshold to be a little further into the acidic range or further into the basic range by holding on. But what buffers do is they hold on to hydrogen ions, and so they will release them if it becomes too basic, so it neutralizes it, or they will hold on to more of them if it becomes too acidic, so sort of neutralizing that as well. So you can see in this picture here, we want to be able to look at solutions like this and say, is that acidic, or is that basic, or is that more of in homeostasis where it's neutral? We can see the picture on the left, you have a bunch of OHs, so that is basic, it's alkaline. In the center, you have basically H2O and H2O there, so it is neutral. It has just as many hydroxide ions as it has hydrogen ions. And then on the right side, you see a bunch of hydrogen ions. So that's acidic. And so it wants to be more like the one in the center, neutralized.